Hello everyone, I am Dr. Sonia Juneja, Assistant Professor in Kite Group of Institutions, Ghaziabad. Today I am going to start Maxwell's equation, which covers Maxwell equations, derivation of Maxwell equations in differential form, derivation of Maxwell's equation in integral form, and last, give the physical significance of each equation. Maxwell's equations are the backbone of electromagnetism, basically based on four basic laws like Gauss law of electrostatics, Gauss law of magnetostatics, Ampere's law, and Faraday's law. Maxwell's equations are based on four basic laws: Gauss law of electrostatics, Gauss law in magnetostatics, Ampere's law, and Faraday's law. The differential form of Maxwell's equation is, the first equation is del dot D, means divergence of D is equal to rho, and the integral form is surface integration of D dot ds is equal to Q, where D is the electric displacement vector, rho is the volume charge density, Q is the total charge enclosed with the surface. And the second Maxwell equation is del dot B, means divergence of B is equal to 0, and the integral form of second equation is surface integration of B dot ds is equal to 0, where B is the magnetic induction. Third Maxwell equation is curl of E, means del cross E is equal to minus del B over del T, and the integral form is line integral of E dot dl is equal to minus surface integration of del B by del T dot ds, where E is the electric field intensity and B is the magnetic induction. And the fourth differential equation is del cross H, or curl of H, which is equal to J plus del D over del T, and the integral form of fourth equation is line integral of H dot dl is equal to IC plus ID, where H is the magnetic field intensity, IC is the conduction current, and ID is the displacement current, and J is the current density. Then the derivation of Maxwell equation in differential form, we derive Maxwell first equation, which is del dot D, or divergence D is equal to rho. This equation is obtained by the application of Gauss law of electrostatics. D is the electric displacement vector and rho is the volume charge density. We know that Gauss law of electrostatic is surface integration of E dot ds is equal to Q by epsilon naught. Multiplying by epsilon naught on left hand side, then epsilon naught E into ds is equal to Q. Then epsilon naught E becomes D, electric displacement vector, then surface integration of D dot ds is equal to Q. If rho is the volume charge density, then we know that Q is equal to volume integration of rho dV, because rho is the volume charge density, charge per unit volume. Then total charge becomes is equal to volume integration of rho dV. Substituting the value of Q here, we have surface integration of D dot ds is equal to volume integration of rho dV. Applying Gauss divergence theorems on the left hand side of above equation, we have volume integration of divergence D into dV, surface integration converted into volume integration and becomes volume integration of divergence D into dV, which is equal to volume integration of rho dV. Then it becomes volume integration of divergence D minus rho into dV is equal to 0. dV cannot be 0 because dV is the volume element, which implies divergence D minus rho is equal to 0. Then divergence D is equal to rho, which is the Maxwell first equation. This is the differential form of Maxwell first equation. Now Maxwell second equation is divergence of B, or del dot B is equal to 0. This equation is obtained by the application of Gauss law of magnetostatics, where B is the magnetic induction. B is the magnetic induction, and this equation is obtained by the Gauss law of magnetostatics. We know that Gauss law of magnetostatics is surface integration of B dot ds is equal to 0, where surface integration of B dot ds is the magnetic flux. Applying Gauss divergence theorem on the LHS of above equation. Then the surface integration converted into volume integration. Then volume integration becomes divergence B dV is equal to 0. dV can't be 0, therefore divergence B or del dot B is equal to 0, which is the differential form of Maxwell's second equation. Now Maxwell third equation, which is curl of E or del cross E is equal to minus del B by del T. It is obtained by the application of Faraday's law of electromagnetic induction, where B is the magnetic induction and E is the electric field. We know that Faraday's law of electromagnetic induction is EMF is equal to minus d phi by dt. EMF is equal to minus d phi by dt, where phi is the magnetic flux, and from the second equation we know that phi is the surface integration of B dot ds, and the integration form of EMF is line integral of E dot ds. Then the Faraday law becomes line integral of E dot dl is equal to minus d by dt of surface integration of B dot ds. Then line integral of E dot dl is equal to minus surface integration of del B by del T dot ds. When integration changes with d by dt, then d by dt converted into del by del T. Applying Stokes' theorem on the left hand side of above equation, then this line integral converted into surface integral. Then the surface integration is surface integration of curl of E dot ds instead of line integral of E dot dl. Then the surface integration of E dot ds is equal to minus surface integration of del B by del T dot ds. Then surface, which implies surface integration of curl of E plus del B by del T dot ds is equal to 0. ds can't be 0. Therefore, curl of E plus del B by del T is equal to 0, which implies curl of E is equal to minus del B by del T, which is known as Maxwell's third equation. Now Maxwell's fourth equation. Maxwell's fourth equation is curl of H or del cross H is equal to J plus del D over del T. This equation is obtained by the application of modified Ampere's law, where H is the magnetic field intensity, J is the current density, and D is the electric displacement vector. We know that from the Ampere's law, line integral of H dot dl is equal to I, where I is the total current, which is equal to surface integration of J dot ds. Then line integral of H dot dl is equal to surface integration of J dot ds. Again applying Stokes' theorem on the left hand side of above equation, then this line integral becomes surface integral. Then the surface integration of curl of H dot ds is equal to surface integration of J dot ds, which implies surface integration of curl of H minus J dot ds is equal to 0. That is, ds can't be 0, which implies curl of H minus J is equal to 0. But this equation is true for static field only. It is insufficient for time varying field. Therefore, Maxwell substituted J plus JD instead of J. Then this equation can be written as, according to Maxwell, curl of H is equal to J plus JD instead of J. Curl H is equal to J plus JD instead of J. Then taking divergence on both sides, then divergence of curl of H is equal to divergence of J plus JD. Then we know that the divergence of curl of vector H is equal to 0. Then 0 is equal to divergence of J plus JD. Then from the Maxwell first equation we know that divergence D is equal to rho and divergence JD is equal to del rho by del T. Then when 0 is equal to divergence J is equal to divergence J plus JD, then divergence J is equal to minus divergence JD. From the equation of continuity we know that divergence J is equal to plus del rho by del T. And from the Maxwell first equation, divergence D is equal to rho. Then we have divergence JD is equal to del by del T of divergence of D. Then divergence of JD is equal to divergence of del D over del T. Then that implies JD is equal to del D over del T. Substituting the value of JD in this equation, we have curl of H is equal to J plus del D over del T in the place of JD. Then the Maxwell fourth equation becomes curl H is equal to J plus del D over del T. This is the differential form of Maxwell fourth equation. Now second part is derivation of Maxwell equations in integral form. The integral form of Maxwell first equation is surface integration of D dot ds is equal to Q. We know that the differential form of Maxwell first equation is divergence D is equal to rho del dot D is equal to rho. If we integrate this equation over the volume V, we have volume integration of divergence D into dV is equal to volume integration of rho dV. From the previous article, we know that volume integration of rho dV is equal to Q. Then volume integration of divergence D into dV is equal to Q. Applying Gauss divergence theorem on the LHS of this equation, we have surface integration of D dot ds is equal to Q. This is the integral form of Maxwell first equation, which says that the total electric displacement, surface integration of D dot ds means total electric displacement through any closed surface is equal to the total charge enclosed with it. The total electric displacement through any closed surface is equal to the total charge enclosed with it. Now, integral form of Maxwell second equation is surface integration of B dot ds is equal to 0. We know that the differential form of Maxwell's second equation is divergence of B or del dot B is equal to 0. If we integrate this equation over the volume V, we have volume integration of divergence B dV is equal to 0. Applying Gauss divergence theorem on this equation, we have surface integration of B dot ds is equal to 0. This is the integral form of Maxwell's second equation, which says that the total magnetic flux, surface integration of B dot ds means total magnetic flux through any closed surface is equal to 0. Means monopole cannot exist. Means north and south pole both are exist in the magnet if surface integration of B dot ds is equal to 0. Magnetic field lines makes a closed loop, means monopole cannot exist. The integral form of Maxwell third equation is line integral of E dot dl is equal to minus surface integration of del B by del T dot ds. We know that the Maxwell third equation is curl of E is equal to minus del B by del T. Integrating this equation over the volume S, over the surface S, then surface integration of curl of E dot ds is equal to minus surface integration of del B by del T dot ds. Applying Stokes theorem on the LHS of this equation, then we have line integral of E dot dl, this surface integral converted into line integral. Then we have line integral of E dot dl is equal to minus surface integration of del B by del T dot ds. This is the integral form of Maxwell third equation, which signifies that changing magnetic field produces electric field. Maxwell third equation states that changing magnetic field produces electric field. Now Maxwell fourth equation integral form is line integral of H dot dl is equal to IC plus IT. Then we know that the differential form of Maxwell fourth equation is curl of H is equal to J plus del D over del T. Integrating this equation over the surface S, we have surface integration of curl of H dot ds. Then surface integration of J plus del D over del T dot ds. Applying Stokes theorem on the LHS of above equation, then we have line integral of H dot dl, this surface integral converted into line integral. Then line integral of H dot dl is equal to surface integration of J plus del D over del T dot ds. Then line integral of H dot dl is equal to surface integration of J dot ds plus del D by del T dot ds. J dot ds is the conduction current and del D by del T dot ds is the displacement current. Then the Maxwell fourth equation integral form becomes line integral of H dot dl is equal to, this is conduction current IC, this is displacement current ID. Then the integral form of Maxwell fourth equation is H dot dl is equal to IC plus ID, which signifies that not only conduction current, displacement current also produces magnetic field. Thank you so much. If you have any query, kindly mail me at sonia.juneja@chi.edu. Thank you.